Ceramics are a class of inorganic and non-metallic materials that are shaped through various forming process and then fired at high temperature to meet the intended application. Who would have thought that from this simple decorative artifact, the application of ceramics have propagated in advance through various fields of application: advanced structural ceramics, aerospace, optics, automotive and electrical application, and electronics. But for this video, we will be focusing on the aerospace application, specifically for space application. Good day everyone! Allow us to share with you the use of ceramics in the journey of humans towards space. When did ceramics started to be utilized as space material? The use of ceramics in space application has a long history, dating back to the early days of space race. But believe it or not, the recognition of ceramics as a space material was not initially realized prior to 1950s, wherein a research scientist at the Naval Research Laboratory began exploring ceramics as a potential material for high-temperature applications in rocket engines and missile nose cones. Grasping this idea, in 1958, a material scientist at NASA led research into the use of ceramics for electronic insulation in various applicable applications. With that, the first use of ceramics in space was in the form of alumina insulators for Explorer 1, which was the very first successful US satellite during that time. During the 1960s, ceramic composites were developed specifically for spacecraft heat shields to withstand the extreme temperature experienced during re-entry. One notable ceramic composite used during this time was the Avcoat, which played a crucial role in the heat shield of Apollo spacecraft, ensuring the safety of the entire mission. And with that success, this opens up the gate for the ceramic materials to spread its application as a space component material as shown in 1970s. Wherein various researches was conducted to ceramic materials such as alumina, silicon carbide, and zirconia for various space applications. Another notable breakthrough during this era was the development of the reinforced carbon-carbon composite, which revolutionizes the ceramic technology in the space applications. RCC composite were utilized as heat shields on the space shuttle, enabling them to withstand temperatures exceeding 1000 degrees Celsius during re-entry. Advancement in ceramic materials continued throughout 1980s to 2000s, with a focus on reaction wheels and mirrors for space telescopes. The ceramic were used in the Hubble Space Telescope to create a highly precise, lightweight, and thermally stable structure. The main mirror of the telescope was made of a fused silica, while the secondary mirror itself was made out of beryllium. Ceramics were also used in the construction of the Chandra X-ray Observatory, which is a spacecraft telescope designed to observe the X-ray from high-energy regions of the universe. The mirror of this telescope were made of ceramic materials called X-ray grade silicon. A couple of years forward, a material scientist at NASA led research into the new types of ceramic materials such as nanostructured ceramics and ceramic metal composite for various space applications, including spacecraft propulsion and thermal management system.
And now let us know the applications of advanced ceramics in space. Industrial application. Advanced ceramic materials are widely used in space applications due to their unique characteristics. Here are some of its applications. Number 1. Thermal Protection System or TPS for spacecraft re-entry. Advanced ceramics such as silicon carbide, silicon nitride, and carbon-carbon composites are used as TPS for spacecraft re-entry. These materials have high melting points and excellent thermal shock resistance, which makes them ideal for protecting spacecraft from the extreme heat generated during re-entry. Number 2. Satellite components. Advanced ceramics such as alumina, zirconia, and silicon carbide are used in the manufacture of satellite components such as structural elements, electronic packages, and microwave components due to their excellent mechanical and thermal properties that are suitable for use in the harsh space environment. Propulsion systems. Advanced ceramics such as silicon carbide and silicon nitride are used in the manufacture of components of propulsion systems such as rocket nozzles and heat exchangers. These ceramics have high melting points, excellent thermal conductivity, and chemical stability, which make them suitable for use in high temperature and corrosive environments. Lastly is the energy systems. Advanced ceramics such as solid oxide fuel cells, COFCs, and thermoelectric generators, TEGs, are used in space application for power generation. These ceramics have high thermal and chemical stability, which make them suitable for use in the harsh space environment. Recent application. Ceramic matrix composites or CMCs are for spacecraft structures. CMCs are lightweight and strong materials that can withstand extreme temperatures, making them ideal for spacecraft structures. Number 2. Ceramic thermal protection system for spacecraft. So TPS made of advanced ceramics such as silicon carbide and carbon-carbon composites are used to protect spacecraft from the extreme heat generated during re-entry. Number 3. Ceramic heat exchangers for spacecraft propulsion. Ceramic heat exchangers made of silicon nitride and silicon carbide are used in spacecraft propulsion systems to transfer heat from the hot combustion gases to the propellant. And lastly is the 3D printing ceramics for space programs. Space program scientists have recently used 3D printing to make custom-made technical ceramic components. This is to address a major lateral weak point, which is their inclination to cracking.
The chemical composition and microstructure of ceramics is fundamental in attaining the desired properties intended for space application. Ceramic used for space components are typically made out of refractory oxide and non-oxide materials such as carbides, nitrides, and borides due to their high melting point, thermal stability, and excellent mechanical properties at high temperature. In recent applications, the ceramic matrix composite was the commonly utilized material as space components. Its chemical composition can vary depending on the specific material used for the matrix as well as on its reinforcement component. As an example, the carbon fiber reinforced silicon carbide composite typically have a silicon carbide matrix with a high purity of 99.9% and a carbon fiber reinforcement. Now, in terms of microstructure, it can vary depending on the specific matrix and reinforcement materials used as well as the processing technique employed into it. The carbon fiber reinforced silicon carbide composite, as an example, typically have a crystalline silicon carbide matrix and a unidirectional carbon fiber reinforcement. Another notable example here is the zirconia toughened alumina composite, which is typically composed of zirconium dioxide and alumina with a varying proportions depending on the required balance of strength, toughness, and wear resistance. The microstructure of the zirconia toughened alumina composite typically consists of a fine-grained alumina matrix with zirconia particles dispersed throughout. The zirconia particle serves to toughen the alumina matrix by deflecting or arresting the cracks that forms during the loading, preventing them from propagating and leading to failure. The synthesis process for various ceramic materials utilized for space application typically involves several steps, including material selection, reinforcement selection, manufacturing, testing, and application. In synthesizing the ceramic matrix composite, the silicon carbide, alumina, zirconia was the common matrix materials used into its application, while the silicon carbide fiber, carbon fiber, and the ceramic whiskers was commonly employed as a reinforcement material. On the other hand, there are several manufacturing methods for the ceramic matrix composite, including the chemical vapor infiltration, melt infiltration, and polymer infiltration and pyrolysis. In synthesizing the ceramic thermal protection system components, silica and alumina are commonly used in this field, and they are manufactured either through plasma and thermal spraying, weaving, and casting. This will be then tested in terms of mechanical test, thermal test, and environmental test. For satellite and space-based telescope components, alumina, silica, zirconia, and beryllium was frequently used in this synthesis, then go through its corresponding process and testing. Commonly, telescope mirrors are grinded and polished and are coated for protection. Other components are manufactured using hot pressing and coated using plasma spraying and chemical vapor deposition. And the resulting output will then be tested on its suitable characterization test. Lastly, in manufacturing ceramic heat exchanger, silicon carbide, alumina, and silicon nitride are employed and then go through the process of either hot pressing, slip casting, or reaction bonding prior to its corresponding property test.
Characterization techniques. Advanced ceramic materials must undergo rigorous characterization to ensure that they meet the desired specifications for their intended use. Here are the commonly used characterization techniques in space application. Number 1. X-ray diffraction or XRD. This technique can be used to study the thermal stability, microstructure, and phase transformations of ceramics under different conditions. Number 2. Microstructural analysis. Techniques such as scanning electron microscopy and transmission electron microscopy are used to observe the grain size, porosity, and defects in the ceramic material, which are important for understanding the material's mechanical and thermal properties. Number 3. Infrared spectroscopy. This technique helps to identify the presence of various functional groups such as metal oxide bonds and provides information on the material's thermal stability and oxidation behavior. Number 4. Raman spectroscopy. So this technique is used to study the crystal structure, defects, and bonding in ceramics. Number 5. Atomic force microscopy or AFM. So this technique is used to study the surface morphology and topography of ceramics. Thermal analysis. So thermal analysis such as the differential scanning calorimetry and the thermogravimetric analysis are used to determine the thermal stability, specific heat, and thermal conductivity of materials. And lastly is the mechanical testing. So this technique is used to determine the material strength, toughness, and fracture behavior under various loading conditions. So there are many properties of ceramics that make them desirable for space application. So first is high strength and durability. So advanced ceramics are extremely strong and can withstand high levels of stress, making them ideal for use in space applications where materials must endure harsh environments. Advanced ceramics have flexural strengths ranging from 300 megapascal to 1.4 gigapascals, depending on their processing method. Number 2. Lightweight. Advanced ceramics are lightweight, which makes them ideal for use in space application where minimizing weight is crucial for reducing launch cost and increasing payload capacity. So advanced ceramics are lightweight materials with a density ranging from 2.8 grams per cubic centimeter to 3.97 grams per cubic centimeter. Number 3. High thermal resistance. So advanced ceramics have excellent thermal resistance and can withstand extreme temperatures without degrading or melting. So this property is crucial for space application where materials must endure rapid and extreme temperatures changes. Advanced ceramics can withstand temperatures up to 1,600 degrees Celsius to 2,200 degrees Celsius in air and 2,000 to 2,600 degrees Celsius in vacuum. Fourth is the corrosion resistance. Advanced ceramic can withstand exposure to harsh chemicals and environmental conditions, making them ideal for use in space application where materials must be able to withstand prolonged exposure to the harsh conditions of space. Number 5. Electrical and magnetic properties. Some advanced ceramics have unique electrical and magnetic properties that make them ideal for use in space applications such as sensors, actuators, and communication devices. Number 6. Low thermal expansion. So advanced ceramics have a low coefficient of thermal expansion or CTE, which means that they do not expand or contract significantly with changes in temperatures. Advanced ceramics have low coefficients of thermal expansion ranging from 4.8 times 10 raised to negative 6 per degree Celsius to 7.2 times 10 raised to negative 6 per degree Celsius. Number 7. Radiation resistance. Advanced ceramics are also highly resistant to radiation damage, making them ideal for use in space application where exposure to radiation is a concern. Advanced ceramics have high radiation resistance with the ability to withstand ionization radiation levels up to 1 times 10 raised to 7 gray to 1 times 10 raised to 8 grays.
In recent studies, various material scientists and engineers are constantly exploring other applications of ceramics in space and are constantly improving the properties of the existing ones. In the study of the thermal properties and ablation performance of a ceramic matrix composite which was reinforced with zirconium fiber, Their findings indicates that these ceramic composite have excellent thermal stability and resistance to ablation, making them suitable for high temperature application in space. On the other hand, a researcher is exploring the use of terrestrial rock in fabricating a porous ceramic material, and this was characterized to have a high porosity and a good mechanical properties, making them a potential candidate for structural application in the moon. And lastly, a researcher developed a ceramic-based heat exchanger for use in space nuclear application system. The heat exchanger was made from a silicon carbide and demonstrate excellent thermal and mechanical properties as well as corrosion resistance in the harsh space environment.
And now for the last part is the annual production cost. Unfortunately, we don't have information about the production cost of advanced ceramics in space applications, but we have provided the market insights of advanced ceramics in space. So, according to Global Market Insights, aerospace insulation market value in 2019 had reached $3.12 billion and is expected to garner 6% compound annual growth rate in 2020 to 2026. So, we have here a figure on the aerospace insulation market. As depicted in the figure, in 2019, ceramic material held over 50% share of the total market value in aerospace insulation. Advanced ceramics have gained popularity in aerospace and aviation design, manufacturing, and development and are used for several applications such as batteries, semiconductors, and magnets for aircraft types. 3D printing is an advanced process used in designing and manufacturing operations. The global 3D printing ceramic market size was valued at $20.6 million in 2018 and is expected to escalate with 34% CAGR from 2019 to 2025. Printing market manufacturers are focusing on the development of new applications related to the three-dimensional print process. So we have here a figure on the US 3D printing ceramics market size by end use 2014 to 2025 in USD million. Based on the report summary presented by the Grand View Research, the aerospace sector is anticipated to grow at a compound annual growth rate of 34.2% in 2019 to 2025 in terms of revenue. The demand in the aerospace application is due to the development of new materials and increasing investments in this emerging field. For instance, in 2017, Nano Dimension raised around $4.8 million to develop 3D printed ceramic parts for the aerospace and defense sector. Are you curious about the world of ceramic engineering? Today, we will take you on a journey through our experiences as ceramic engineering students. Hi, I am Marwan Joy Elhinete, fourth-year ceramic engineering student.
I am Arnel Almignon, a fourth-year BS Ceramic Engineering student,
Join us as we share our experiences.
and shed light to this fascinating aspect of this program.
One of the highlights of our journey as ceramic engineering students has been the immersive hands-on laboratory experiences. Those things provided us students with a remarkable opportunity to dig deep into the intricate world of ceramic materials, unraveling their unique properties and techniques used in their fabrication processes. In the laboratory, we had the chance to work with ceramic samples, carefully preparing them for characterization. From the sample preparation, fabrication process, especially sleep casting, in which we have gained a comprehensive understanding and the complex procedures involved in ceramic production.
Aside from that, conducting testings on ceramic samples has been an enlightening experience. We have explored various characterization techniques, which are essential in investigating the chemical, the physical, the mechanical, the structural, as well as the thermal properties of ceramics. Now, these experiments have allowed us to witness firsthand the intricacies of each ceramic forming process and characterization test, and the situations like what would be the effect of composition and material behavior if we are to increase the amount of this material, and then situations like thermal transformation that we need to account and the each oxide that is found within the composition of our product in order to design an efficient firing curve in preparation for firing our product in the kiln. And furthermore, these laboratory experiences have equipped us with invaluable technical skills, scientific curiosity, and the ability to apply our knowledge learned from the theories taught by our faculties in a more practical and real-world situations.
But our education isn't limited to school setup. As part of the ceramic engineering course, we have the opportunity to work in the industry setting. Through our on-the-job training and plant tour, these hands-on experiences gave us a chance to apply our knowledge in the real world, working alongside professionals in ceramic industries. It has not only expanded our practical knowledge but has also provided valuable insights into manufacturing processes, quality control, and the development of innovative ceramic products.
Participating and attending lectures and webinars has been another transformative aspect of me being a ceramic engineering student. Those opportunities have connected us students with the experts in the field of ceramics and provided a platform to exchange ideas and gain ideas and experience from them. Now, the interaction and networking during these events have broadened our perspective and inspired us with new possibilities and helped us envision the diverse career path available within the world of ceramics and not just the typical kaang maker that others are stereotyping. On the other hand, another aspect that greatly enriched my experience during my 4-year course here is that I was able to get involved in social activities such as Minaholmet, Ceramic Engineering Week, and even Palakasan in institute-wide events. Now, these events have provided me an opportunity to connect with my fellow students, as well as my faculty members, and industry professionals in some events on a more personal level. Now, the moments shared during these occasions have fostered a sense of camaraderie and a deeper understanding on the field that I am in beyond the confinement of the textbook and classrooms. Through this course also, I have met such diverse people which I was able to be acquainted with, and some of which really became close to me. Now, the friendship forged during these late night study sessions and group projects not only made the learning process more enjoyable, but also create a network of like-minded individuals who share the same passion when it comes to ceramic engineering. Collectively, all those experiences, opportunities, and challenges have molded us into a skilled and versatile ceramic engineering student. The rewards have come into the form of personal growth, an expansion of knowledge, and also this confidence that we have to contribute meaningfully to the field of ceramics.
Ceramics is more than just pottery. It is a diverse and dynamic field where the future is shaped by developing materials that enhance technology, improve sustainability, and revolutionize industries. I am Rowana Johinete, a BS Ceramic Engineering student.
I am Arnel Alminion, a proud BS Ceramic Engineering student saying,
And we mold great.
we mold greatness.